Calculate the mass of hydrogen gas required to produce 500 kilograms of ammonia using Haber's process. In Haber's process, ammonia is synthesized from nitrogen and hydrogen. And the molecular formula of ammonia is NH3. Now, if you look at this, you would understand that all the nitrogen and hydrogen consumed during this reaction are ending up in ammonia because it is the only product in this reaction. There is no other product here. So, this nitrogen and hydrogen have nowhere else to go. So, that means the mass of hydrogen gas consumed is equal to the mass of hydrogen in the ammonia formed. Law of conservation of mass, right? So, because mass of hydrogen in the ammonia formed is exactly equal to the mass of hydrogen gas consumed during that reaction, to get the mass of hydrogen gas required to produce so much ammonia, all we need to figure out is the mass of hydrogen present in so much of ammonia. Now, what is the mass of 1 mole of ammonia? Molecular formula is NH3, so it would be 14.0 plus 3 times 1.0, and the relative molecular mass expressed in grams is the mass of 1 mole of that substance. So it is 17.0 grams. Out of 17.0 grams of ammonia, there is 3 grams of hydrogen. So, to produce 17 grams of ammonia, you would need 3 grams of hydrogen, right? Because the mass of hydrogen present in ammonia is equal to the mass of hydrogen consumed in this reaction. But how much ammonia are we looking for? 500 kilograms. So 500.0 times 10 to the power of 3 grams of ammonia requires how much hydrogen? So to get this, you have to multiply 500.0 into 10 to the power of 3 grams with 3.0 grams over 17.0 grams. You cancel these two and simplify this to get the mass of hydrogen gas required in grams, and divide that with 10 to the power of 3 to get the mass of hydrogen gas in kilograms. See, the point you must notice here is, here we answered this question without using a balanced chemical equation. We did not even write a chemical equation here. In this case, we simply applied the law of conservation of mass to one of the elements in the reaction that we are interested in. And by applying the law of conservation of mass to a part of the reaction that we are interested in, we are able to answer this question. So understand that you don't always require a full balanced equation to answer some of the stoichiometric questions. You will understand that better in the next example. What do we have next? White phosphorus is prepared by fusing calcium phosphate with carbon and sand in an electrical furnace. If all the phosphorus in calcium phosphate is converted into white phosphorus, calculate the mass of calcium phosphate required to make so many grams of phosphorus. So here we have three reactants, calcium phosphate plus carbon plus sand is nothing but silicon dioxide. So we know all the reactants of this reaction, but we know of only one product, that is white phosphorus. There must be some other products here, right? But I do not know what they are. So I will not be able to write a complete chemical equation for this reaction. So obviously I cannot write a balanced chemical equation for this reaction. Still, I have to answer this question. How can I do that? Now there is a clue in the question, that is, if all the phosphorus in calcium phosphate is converted into white phosphorus. See, on the reactant side, this is the only compound that has phosphorus, and the question says that all the phosphorus present here is getting converted into white phosphorus. It is not going anywhere else. Then calculate the mass of calcium phosphate required to make 6.5 grams of white phosphorus. So what is the mass of calcium phosphate required? Now typically we answer these questions by using a balanced chemical equation. We figure out the stoichiometric coefficients. The stoichiometric coefficients give us a relationship between their masses, and using that relationship we figure out the answer to such questions. But here I don't have a balanced chemical equation. But as we did in the previous question, we don't need a balanced chemical equation to answer this question. See, from the question we can understand that we are not interested in the masses of all the reactants and products involved in the reaction. We are given the mass of white phosphorus that we need to make, and we are asked to calculate the mass of calcium phosphate required for that. So let us write down the part of the chemical reaction that we are interested in. Now, among the reactants, calcium phosphate is the only source of phosphorus, and there is no phosphorus elsewhere. And it is given in the question that all the phosphorus present in calcium phosphate is getting converted into white phosphorus. It is not going anywhere else. Because of this, when you apply law of conservation of mass, you can understand that the mass of phosphorus in calcium phosphate must be equal to the mass of white phosphorus produced, right? All the phosphorus present in calcium phosphate is ending up as white phosphorus, and there is no other source of phosphorus among the reactants. So that obviously means, according to law of conservation of mass, mass of phosphorus present in calcium phosphate must be equal to mass of white phosphorus produced. And what is the mass of white phosphorus we have to produce? 6.5 grams of white phosphorus. Then that is the mass of phosphorus present in calcium phosphate. So what you have to figure out now is the mass of calcium phosphate that contains 6.5 grams of phosphorus. Now what is the mass of 1 mole of calcium phosphate? It is 3 times 40 plus 1 times 31 plus 4 times 16, this whole thing twice in grams, right? So this is the formula weight of calcium phosphate expressed in grams would be the mass of 1 mole of calcium phosphate. I think upon simplification this comes to be around 310 grams. Now in 310 grams of calcium phosphate, how much phosphorus is there? 2 times 31, right? So 2 times 31 grams. So if you want 2 times 31 grams of phosphorus, you have to take 310 grams of calcium phosphate, right? But we are producing 6.5 grams of phosphorus. So for that, how much calcium phosphate is needed? So the mass of calcium phosphate needed to produce 6.5 grams of white phosphorus would be 6.5 grams multiplied with 310 grams over 2 times 31 grams. Cancel these two units and simplify this to get the mass of calcium phosphate in grams. So you have to take so many grams of calcium phosphate to make 6.5 grams of white phosphorus. So again, we answered this question without a balanced chemical equation. Just by applying the law of conservation of mass to the part of the reaction that we are interested in. Now let us work out another example. In the quantitative analysis of phosphorus, an aqueous solution containing monosodium phosphate was treated with magnesium and ammonium ions in an aqueous solution. The magnesium ammonium phosphate precipitated in this reaction was thermally decomposed to magnesium pyrophosphate and its weight was found to be 2.103 grams. Calculate the mass of monosodium phosphate present in the aqueous solution originally. So we are given the mass of this product and we are asked to figure out the mass of this reactant that we started with. Here are two equations for the reactions this question is talking about, and they are balanced chemical equations as far as I can tell. Though we have two equations here and they seem scary when we look at them, understand the fact that we are not interested in all these reactants and products. Here we are doing a quantitative analysis for phosphorus. Now, among the reactants that we have taken, phosphorus is present only in monosodium phosphate, that is here. It is not present anywhere else. And eventually, all that phosphorus is ending up in magnesium pyrophosphate, that is this. And see, there is no phosphorus anywhere else. So if you look at these two equations, you would understand that monosodium phosphate that we have taken is eventually either in one step or in two steps, it doesn't matter. Eventually it is getting converted into magnesium pyrophosphate, and all the phosphorus present here is ending up here, and we are given the mass of this magnesium pyrophosphate formed, and we are asked to figure out the mass of sodium monosodium phosphate that we started with. And this is similar to the questions we have done before. So To answer this question, we don't have to look at all the reactants and products or the balanced chemical equation. We can apply law of conservation of mass only to this part of the reaction that we are interested in. Can you give it a try? Now let us say we started with some x grams of monosodium phosphate and we eventually ended up with 2.103 grams of magnesium pyrophosphate. And as we can understand from these equations, all the phosphorus originally present in monosodium phosphate is ending up in magnesium pyrophosphate. Now if we apply law of conservation of mass, that means mass of phosphorus in x grams of monosodium phosphate must be equal to mass of phosphorus in 2.103 grams of magnesium pyrophosphate, right? That's what we just discussed. Now from here you can do one thing. You can figure out the mass of phosphorus in 2.103 grams of magnesium phosphate because you know its formula. You can calculate the mass of phosphorus in so many grams of this compound as we did earlier, and then figure out the mass of monosodium phosphate that contains the same amount of phosphorus. This is how we solved the previous question, right? Now let us do this slightly differently. If the mass of phosphorus in x grams of monosodium phosphate and so many grams of magnesium pyrophosphate is the same, then the number of atoms must also be same, right? So number of atoms of phosphorus in x grams of monosodium phosphate is equal to number of atoms of phosphorus in so many grams of magnesium pyrophosphate. Now how do we calculate the total number of phosphorus atoms in x grams of this compound and in 2.103 grams of this compound? Remember, x grams and 2.103 grams are masses of these two compounds respectively. We can do that. We have done similar examples before. From the formula of this compound, we can understand that its formula weight is approximately 120. So 1 mole of this compound weighs approximately 120 grams. Similarly, the formula weight of this compound is 222.5 and 1 mole of this compound weighs 222.5 grams approximately. Now here we have x grams of this compound. If you divide the given mass with the mass of 1 mole, you will get the number of moles. So number of moles of NaH2PO4 in x grams of that substance is x grams over 120.0 grams. Similarly, the number of moles of Mg2P2O7 in 2.103 grams of that compound is given mass over its molecular weight in grams, formula weight in grams, this is an ionic compound, so it would be 222.5 grams. Cancel these two. So we got the number of moles of these two compounds. Now, how many formula units are there in so many moles? To get the number of formula units, you have to multiply the number of moles with Avogadro's number, right? So the number of formula units of NaH2PO4 in X grams of that compound is X over 120.0 multiplied with N. Similarly, this is also an ionic compound, so number of formula units of Mg2P2O7 in 2.103 grams of that substance is, you have to multiply this number of moles with Avogadro's number. Now these are the formula units of monosodium phosphate. These are the formula units of magnesium pyrophosphate. But what we are looking for is the number of atoms of phosphorus. See, in each formula unit there is only one phosphorus atom. So if you have so many formula units, how many phosphorus atoms would you have in all of them put together? You have to multiply it with 1, right? Because in each formula unit there is only one phosphorus atom and we have so many such formula units. So the total number of phosphorus atoms in X grams of monosodium phosphate is X over 120.0 times N times just 1, because per formula unit there is only one phosphorus atom. Now what about this? In each formula unit here we have two phosphorus atoms and you have so many such formula units. So total how many phosphorus atoms are there in 2.103 grams of Mg2P2O7? In this mass of this compound there are so many formula units and each formula unit has two phosphorus atoms. So to get the total number of phosphorus atoms, you have to multiply this whole thing with 2. That is 2.103 over 222.5 times N times 2. And according to this, these two must be equal, right? 1 and 2. So now let us equate these two. So that is X over 120.0 times N times 1, that is 1, is equal to 2.103 over 222.5 times N times 2, that is 2, right? Now you can cancel these two and simplify this to get the value of X. You will get a dimensionless number here, and the mass of this compound, that is monosodium phosphate, is X grams. So you have to express this value of X in grams to get the mass of monosodium phosphate that you started with. So again, we solved this problem without using these balanced equations. We considered only that part of the reaction that we are interested in, and we did not even balance this, but we simply applied the law of conservation of mass, and from that we applied the principle of atom conservation to solve this problem. Though we did not balance the equation by putting some coefficients here, we are actually doing the same here. So without putting the coefficients, we are balancing only the part of the reaction that we are interested in. Now what do we have next? Blister copper is produced by the reaction between cuprous oxide. It is Cu2O. You must know its formula, and cuprous sulfide is Cu2S. And it says all the copper present in these two compounds is extracted as blister copper, and when they took a mixture of 1.0 grams of cuprous oxide and cuprous sulfide, the mass of copper extracted is 0.85 grams, and it is given in the question that all the copper present in these two compounds is ending up as blister copper. It is not going anywhere else. Then what is the mass of cuprous oxide? Again, we don't have to worry about the balanced chemical equation, because it is given that all the copper present in these two compounds is ending up as blister copper. Now by applying law of conservation of mass to copper, we can say that, now let us say in 1.0 grams of this mixture, x grams is cuprous oxide, then cuprous sulfide would be 1 minus x grams, right? The total mass of the mixture is 1 gram. So if we assume that the mass of cuprous oxide is x grams, obviously the mass of cuprous sulfide must be 1 minus x grams. So now by applying law of conservation of mass to copper, we can say that total mass of copper in x grams of cuprous oxide plus total mass of copper in 1 minus x grams of cuprous sulfide must be equal to mass of copper extracted, right? That's what is given here. All the copper present in both these compounds is ending up as blister copper, and its mass is given here. So it must be equal to 0.85 grams. Now if the total mass of copper present in these two compounds is equal to the total mass of copper extracted, then the number of atoms must also be equal, right? That means total number of copper atoms in x grams of cuprous oxide plus total number of copper atoms in 1.0 minus x grams of cuprous sulfide must be equal to total number of copper atoms in 0.85 grams of copper. Now how do we figure out the total number of copper atoms in x grams of cuprous oxide? Now by dividing the mass given with the formula weight of cuprous oxide in grams, what would that be? 63.54 times 2 plus 16. Now is it 8, 1, 7, 12 plus 16, right? Is it approximately 143 expressed in grams is the total number of moles of cuprous oxide. To get the total number of formula units of cuprous oxide, multiply it with Avogadro's number. And if you want to get the number of copper atoms, in each formula unit of cuprous oxide there are 2 copper atoms, so you have to multiply it with 2. Similarly here, what is the total number of moles of cuprous sulfide? It would be 127.08 plus 32. Is it 159.08? So divide the mass given with the formula weight of that substance in grams. It is 159.08 or 159.0 grams approximately. You would get the number of moles of cuprous sulfide. To get the number of formula units of cuprous sulfide in so many moles of cuprous sulfide, you multiply it with Avogadro's number. Then in each formula unit there are 2 copper atoms, so multiply it with 2. So this is the total number of copper atoms in 1 minus x grams of cuprous sulfide. This is the total number of copper atoms in x grams of cuprous oxide. Then how many copper atoms are there in 0.85 grams of copper? 0.85 grams over 63.54 grams, right? Given mass over the relative atomic mass of copper in grams, that is 1 mole of copper multiplied with Avogadro's number, as simple as that. So cancel these and solve this for x to get and express that in grams to get the mass of cuprous oxide in this mixture. And we can come up with any number of similar questions. We may say that we have a mixture of 2 hydrocarbons and the mass of the mixture is so many grams, and upon complete combustion so much carbon dioxide is produced. Then what is the mass of one of the hydrocarbon in the mixture of 2 hydrocarbons? Same logic, because upon complete combustion all the carbon present in both the hydrocarbons would end up in carbon dioxide. It is not going anywhere else. So you are given the mass of the carbon dioxide, so from that you can figure out the mass of carbon. Then all the carbon must have come from both these hydrocarbons. So by using a similar logic you can figure out the mass of one of the hydrocarbons, and you can come up with any number of similar questions. But understand the concept and you will be able to apply it in different situations.